All right, Algebra 2. Today we're going to talk about 4.4 about complex numbers. This is a combination of imaginary numbers mixed with real numbers. So when you combine those, you get complex numbers. All right, so today's lesson is really on imaginary numbers. The name imaginary numbers just doesn't set well with most people. So even we haven't changed that yet. It's still called an imaginary number, but they are very real, just not in our real number system. Okay, so first off, like if you were to consider this polynomial right here, if you guys try to factor this, try to find the roots, you're not going to find anything. Two things that multiply to give you 4, add to give you 2, there's going to be nothing there. So this thing is not going to cross the x-axis, therefore we say there's no real solution. There's no real root, right? But it turns out that there is a root. It's just in another numerical dimension. All right, so that's what we're going to unpack for today. So in order to unpack that, we got to start with the basics of what an imaginary number is. So an imaginary number, or an imaginary unit, is simply the square root of a negative number. Okay, so if you have the square root of -1, that is equivalent to I. And as you can see here, if you square both sides of that to try to get rid of the radical, you would get I squared is equal to -1. All right, so these two definitions are going to be used to build your whole understanding of i's and i's to various powers here in a couple slides. So let's start off with a couple of examples here. If I have something like the square root of -18, all right, obviously you plug that into your calculator, you're going to get, an error or something like that. But today, what you're going to do, don't use a calculator, just break this down into its simplest parts. So just a reminder, if you have something in a radical, you have to pull out the perfect squares. Perfect squares being, 2 squared, 3 squared, 4 squared, 5 squared. All of these things, like these are perfect squares, right? So 4, 9, 16, 25. Feel free to write a bunch of them down if you want to use them, but you should just start to see those perfect squares when they exist. But if you don't, feel free to write a bunch of them down. But here we go. For this one, I can rewrite this as the square root of -1 times the square root of 9 times the square root of 2. Okay, -1 times 9 times 2 is -18. Right, so I can rewrite it that way. And the square root of -1 we know is now I. The square root of 9 is 3, and we can't do anything with this guy, the square root of 2. So that stays square root of 2. Now we always write this a little different. We write it as 3i root 2. The I always comes second. So that would be your answer. So go ahead and try out 1b. Try to simplify that one down. Let's see what we got here. We got square root of -1 times the square root of 25 times the square root of 5. This becomes 5i root 5. Okay, so some properties of I. We already talked about the fact that I to the first power, anything to the first power is just itself, right? So I to the first power is just I. So what I want to show you guys is this. A lot of times for people to understand this, we look at this like on a coordinate plane in which we have a real axis and an imaginary axis. Okay, each power is just a rotation on this. We go from imaginary to real to imaginary to real to imaginary to real. It oscillates kind of back and forth. So if you start with I, okay, I to the first power is simply I. So let's say we start here. Okay, this is our starting place at I, which is a little different than our typical place that we would start on the real coordinate plane. But if we start there, and we go counterclockwise, we always are working counterclockwise. And so if we go counterclockwise this way, Okay, so this is I to the first power. I to the second power would be on the real number system, and it would be at -1. We already proved that I squared is -1. Okay, so this would be -1 is the same thing as I squared. Then I to the third would be, if that's I up here, it would be -I. Okay, so that's the same thing as I to the third, just so you know here, is equal to I squared, which we know is -1, times I. So -1 times I is -I. Okay, then we keep going. Okay, now we bounce back to the real. So I to the fourth is the same thing as 1, because I to the fourth, as you see up here, is just, that is equal to I squared times I squared. I squared is -1. -1 times -1 is equal to 1. Okay, so, and then we just keep going around. So the thing to note here is that every 4 powers we are at a 1. What that means is if I have something like I to the 13th power and I ask you what is that equivalent to? Well, if you have I to the 12th, that's just 3 full rotations around, right? So 3 times 4 is 12, right? So I to the 12th is equal to 1. So this is equivalent to I to the 12th times I. Anything to a power that 4 goes into is equivalent to 1. So this is the same thing as 1 times I, which is equal to just I. So I to the 13th simplifies to I. And then you'll notice things like, well, if we did I to the 14th, that's equal to I to the 12th, that's 1, times I squared. Well, we know that I squared is equal to -1. So this is like 1 times -1, which is equal to -1. So I to the 14th power is equal to -1. Okay, so those are some properties of I. If I said I to the 99th on a test, here's another thing that you could do. Well, we could say, if you think about this as in terms of this coordinate plane here, the real and imaginary coordinate plane, I to the 99th is the same thing as I to the 100th minus 1, right? So I to the 100th we know is a 4, so that would be here at 1 if you were at I to the 100th. So if we go back 1, we'd be at -I. So I know this is -I, but another way that you could find that is you could say, if you want just one system, you could say, okay, 4 goes into that. Let's see, it would be, well, this is the same thing as 96, right? I to the 96, and a 4 goes into I to 96, so that's equivalent to 1. And then you would say times I to the third. Okay, I to the third is the same thing as, so now this is just 1, so this goes away. Okay, so now we've broken it down to I to the third. I to the third is equal to I squared times I. I squared is -1. -1 times I is -I. So either way you look at it. Okay, so some people like to have this in the back of their mind, so they can think about it in terms of rotations. All right, let's look at example 2. So for example 2 here, we have 3i times 4i, which gives me 12i squared, right? So what happens to I squared? I squared becomes a -1. So we have 12 times -1, which is equal to -12. So sometimes when we have two i's, well, when we have two i's, we're going to bounce from the imaginary realm back into the real number system. All right, so 2b. For 2b, notice here that we can, by the way, if you want to break this down ahead of time so you don't have to do some like big math here, and you want to do this in your head, you can write this as square root of -1, square root of 5, square root of 4, and then this one can be broken down as square root of -1, square root of 3, square root of 4. This becomes, this guy goes to a 2, this goes to an I, so it's 2i root 5 times, this one's a 2, this one's an I, 2i root 3. Okay, there's i's in both here, so I'm going to end up with 4i root 15. Right, so 2i times 2i is 4i squared, I should say. Square root of 5 times square root of 3 is square root of 15. I squared we know is -1, so this just becomes -4 root 15. I know these are a little bit tricky. And then 2c, this is what we were just doing. I to the 31st power. Okay, you can write that as, well, let's take out 4. So if we take out 4, 4 times 7 is 28. So I to the 28th I know is equal to 1. So I to the 28th is 1, so that's gone now. And then we have, if we multiply that by I to the 3rd power, we get 31, right? Because 28 plus 3, when you multiply these exponentials, you add those exponents. So you're left with 1 times I to the 3rd. Okay, well, if you memorized your chart, you know what I to the 3rd is. If you don't, you might have to go back to your basic definition of what to I and I squared. So you could say, okay, I to the 3rd is equal to I squared times I. I squared is -1. -1 times I gives you -I. So for 2c, it all simplifies down to -I. All right, the square root property. We know that we can use the square root properties to solve quadratics when you don't have a middle term, right? So if you have something squared plus or minus something that's a whole number, talking about x squared, obviously we use that can be set to equal 0, and then we can move the 256 over as shown here. Divide by both sides by 4. Take the square root. Remember that when you do that, you have 2 answers, right? Because whenever you take the square root of a variable, that could be a positive or a negative of that thing. So you have to consider both sides. So you have 2 answers. And then you have the square root of a negative number there. Well, now, instead of saying no solution, we can actually say that there is this solution. It's just in the imaginary realm, the imaginary number realm. It's not imaginary, though. It's a very real thing. It's a very real number. So just remember that. This is equivalent to plus or minus 8i. Okay, so here let's do some of those. Let's move this 100 over and try to solve this. So we get 4x squared is equal to -100. X squared is equal to -25. Divide both sides by 4. And then x is equal to plus or minus the square root of -25. If I simplify that, that's plus or minus 5i. All right, let's try another one. I'll let you try this one. We have x squared is equal to -4, right? And then x is equal to plus or minus square root of -4. So then x is equal to plus or minus 2i. All right, complex numbers. This is when you have a real and an imaginary number that cannot be combined. Okay, so like whenever there's a real part of an answer and that's a separate term from an imaginary, we cannot combine these things. Those are not like terms. We can't say, oh, that's 7i. No, that's not 7i. That's 4 in the real number system plus 3 in the other number system. Okay, so since they're in different systems, we can't combine them. So here, we are going to combine like terms when you have multiple parts. Imaginary parts stay separate. Okay, so you solve these separately. So this is kind of interesting. If you have something like this, and it looks very, very difficult, it actually comes out very, very simple. Put all of the real parts together and solve that equation, and then do the same thing with the imaginaries. So, and just make sure that you include everything. So some of my real stuff here, let's just highlight all the real parts of this. So that's real, that's real. The rest of it has an I attached to. So first of all, this is one term, this is a term, this is a term because it's all being multiplied. This is a term, this is a term, this is all one term. Okay, so I'm going to take out those real parts now. So we have 5x plus 1 is equal to 2x minus 2. Then I'm going to take my imaginary parts. 3 plus 2y times I is equal to y minus 6 times I. Okay, so let's solve each one of these separately. If I do that here, I get 3x is equal to negative 3, x is equal to negative 1. That's one answer, that's my x. And then for the other one here, if I distribute the I out, I get 3i plus 2yi equals y minus 6 times I, which I guess I can distribute that out. So this will be yi minus 6i. Okay, now let's combine like terms here. If I subtract 3i from both sides, I get 2yi is equal to yi. If I subtracted the 3i from both sides, it would be minus 9i. Then let's subtract yi from both sides. And when I do that, I get yi is equal to, what was it, negative 9i? Okay. So now for this part here, what I'm going to want to do is I'm going to want to divide. I'm trying to find out what y is, right? So I got to divide by I. So if I divide both sides by I get y is equal to negative 9. Okay, the i's canceled out, and I'm done. So I divided by I is just 1. Anything divided by itself is just 1. So we just have negative 9 left. Okay, so here's a couple more for that. So for this guy here, notice that this all acts as one thing, but these aren't being multiplied in here, so I can separate them. Okay, so I can say, I can combine the real parts of this, and I would get negative 1 plus 1, negative 2 plus 1, which is negative 1. And then 5i minus 5i plus negative 7i is going to give me negative 2i. So for 5a, that's all you're doing. You're just combining the real parts with the imaginary parts, combine like terms. Here we have 4 minus negative 1, which is 5. And then we have 6i minus 2, which is positive 4. Okay, so 5 plus 4i. Those go pretty quick. Then for example 6, they get you into like, when do you use this? Well, this is often used in the real world with sine and cosine waves within electronics. So when dealing with voltage, voltage is the equivalent of current, okay, times impedance. So current times impedance in terms of joules here, I believe. So joules is like the imaginary unit. It acts like the imaginary unit. So let's try this out. Impedance. Okay, so I was just looking to see if that is joules. It should be in joules. But anyway, okay, so let's do this. So let's multiply this out. So if I multiply this out, okay, current is equal to 2 minus 4j, which acts like an imaginary number. Okay, so I'm just plugging it into this, and then impedance is 3 minus 2j. And again, the j acts like, I keep wanting to write an I, the j acts like an imaginary number. I don't know why this is not letting me write all of a sudden. Okay, there we go. Sorry guys, apologize. Okay, so let's go ahead and FOIL this out. So if I FOIL this out, 3 times 2 is 6. 2 times negative 2j is negative 4j. Negative 4j times 3 is negative 12j. And then negative 4j minus multiplied by negative 2j would be positive 8j squared. All right, if these act like imaginary numbers now, I can rewrite this as 6 minus 16j, and then j squared, or I squared, is equal to negative 1. So this just becomes minus 8. because if this is a -1 times 8 is -8. Okay, 6 minus 8 gives me -2, so I end up with -16j minus 2. You can write that in any way that you want. You could also write it the other way, but that's okay. And this will be in now volts. Okay. So there's a real-world application of these things. And then finally, man, this is a long lesson, I apologize. Dividing complex numbers using conjugates. Okay, so we got to remember what a conjugate is. A conjugate is simply this, you guys. It's simply multiplying by the same exact set of terms with an opposite sign in between. So I can go over that in class why this is again, why we do this, but you should see it here when I do one. Okay, the big idea is we cannot have an I in the denominator, so we get rid of it. Okay, so we're not allowed to put an I in the denominator. And so to get rid of it, you have to use a conjugate if there's two pieces. If there's a complex number in the denominator, you have to multiply by a conjugate. So if there's a real and an imaginary piece in a denominator, you have to multiply by a conjugate. Okay, so when I do this, let's multiply this out. I get -6i plus, it'll be 2 times 5. -2 times -5 is +10i squared. So it'll be plus 10i squared over, we'll simplify that soon. Then we FOIL this out. We get 9 minus 15i plus 15i. Those go away. That's the whole goal. And then 5 times -5 is minus 25i squared. Okay, this now will simplify. -6i stays the same. 10i squared. I squared is -1, so this just becomes minus 10. Okay, over 9 minus 25i squared. Well, 25i squared is the same thing as -25 because this is -1, right? So it's 9 plus 25 because -25i squared is just -25, which is +25. All right, so this becomes 9 plus 25. Did I do that right? Let me just make sure here. 9 -25 I squared. I squared is -1. Yeah, I think we're good. Okay, so this is 34. -6i minus 10. The reason I was looking is because I know that the final answer is in 17ths, but now that makes sense because this can all be divided by 2. So if I divide everything by 2 here, I get -3i minus 5 over 17. Everything is divided by 2, so I can do that, right? If 2 didn't go into all 3 pieces, then I couldn't do that. And then, you guys, the final thing I need to share with you is this. They always put this in 2 separate terms. This answer is okay, but by convention we put into 2 separate pieces. The imaginary piece, -3i over 17, and the real piece, minus 5 over 17. So by convention they break it up into 2 pieces. All right. And most of the time they write the I as the second term, but I'm okay with you writing it like this. It's totally fine with me. Okay, so that's it, you guys. I'm not going to do the last one with you, but hopefully you will do it, and I'll probably leave it there on the Edpuzzle. I'll start it for you. Okay, FOIL that thing out, simplify it, and we'll see you guys in class.